Hey, welcome back. In this video, we're going to continue to look at generating functions, and we're going to see some more applications of them besides the ones that we saw in the last video. So just to recap, a generating function is just a polynomial that encodes some sequence and its coefficients. And we use the coefficients of a polynomial to encode sequences because sometimes polynomial arithmetic can be useful for determining information about the sequences. When we talked about generating functions in the last video, we used them to count the number of R combinations in multisets. So recall that a multiset, it's like a set, but we're allowed to have repeated elements. So the order of the elements does not matter in a multiset, just like a set. But the difference between a multiset and a set is that a multiset is allowed to have repeated elements. And when we find an R combination of a multiset, this is just R elements of a multiset. So an R combination of a multiset is just like a subset of size R of an ordinary set. In this video, we're still going to do generating functions, but we're going to look at some other kinds of problems besides R combinations. And these problems might seem like more familiar type of problems. So here's one problem where we can use generating functions. Suppose that we have a total of 100 candies, and there's 5 people who want to split the candy. And each of these 5 people has certain rules about the number of candies that they want to get. We'll assume that the first 2 people, both of them want at most 1 candy. So both of them are fine with 0 or 1 candies. The third person, they're fine with any number of candies. So they're okay with 0, they're okay with 1, they're okay with 2, 3, and so on. Finally, the fourth and fifth people, they both have the same rules. They want an odd number of candies. What does that mean? Well, their number of candies needs to be 1, 3, 5, 7, and so on. And the question that we're going to try to answer with generating functions is how many ways are there to split up these 100 candies? And I want to note something here. This 100 here, we'll find the answer for when there are 100 candies, but our solution will work for any number of candies. So for any total, if we have 100, if we have 1,000, if we have 1,000,000,000, any of those, we can use the same solution. And in fact, we can take the second to last step of our solution and read off the number of ways for any number of candies just from that second to last step. So the very last step will just be plugging in 100. The second to last step will have our answer for any possible number of candies. So in order to use generating functions for this candy problem, we're going to make polynomials, and we're going to make one polynomial for each person. The polynomials are going to represent the possible numbers of candies that each person is willing to have. And since the first 2 people have the same rules about the number of candies that they're willing to have, so the first 2 people, both of them want at most 1 candy. So each of them wants 0 candies or 1 candy. And so we can say both of them have the same polynomial. Their polynomial is going to be obtained by taking powers of x. The variable of our polynomial is x. And the powers of x that we'll include in this polynomial are only the powers of x that are numbers of candies that these people are willing to take. And the only numbers they're willing to take are 0 and 1. So we have an x to the 0, we have an x to the 1. And the coefficients next to the x to the 0 and the x to the 1 are just, next to the x to the 0 is the number of ways that person 1 can get 0 candies. And the coefficient next to x to the 1 is the number of ways that person 1 can get 1 candy. Same with person 2, they have the same polynomial. So the 1 right here, this is the number of ways that person 2 can get 0 candies. And the 1 right here, number of ways that person 2 can get 1 candy. When we simplify that, we can just write it as 1 plus x. The x to the 0 is just 1, and 1 times anything is itself. Now we can write a polynomial for the third person. So their polynomial, we'll write it as p sub 3 of x. And since the third person is okay with any number of candies, we'll have every power of x in this polynomial. And every power of x will have a non-zero coefficient. It'll have a 1, because there's one way for the third person to have I candies. Now, when you look at this, you might wonder something. Why are we going to infinity instead of to 100? And the answer is because the solution that we're using here is going to work for any number here, even if this number was much higher, like 1 billion. So we can still use the same polynomial for the third person, regardless of what the number is here. The number up here in the first bullet has no effect on the rules for the third person, that they want any number of candies. So this polynomial for the third person, it's only encoding the third person's rule. It's not encoding the number of candies in the first bullet. So this is the polynomial for the third person. It's 1 times x to the 0 plus 1 times x to the 1 plus 1 times x to the 2, and so on forever. And we can write that as a sum I equals 0 to infinity of x to the I. And now we just have to do the polynomials for the fourth and fifth people. We see the fourth and fifth people, they want an odd number of candies. So an odd number, it's like 1, 3, 5, 7, 9, and so on. So any powers of x that are odd have a 1 coefficient next to them. So the 1 power, the 3 power, the 5 power, all of them have 1s next to them. Any powers of x that are even powers, they have 0 coefficients next to them. And when we multiply something by 0, we get 0. And we add 0 to something, it doesn't change it. So we haven't written any of the terms with 0 coefficients because they're just adding 0 to our polynomial. So the only non-zero terms we have are 1 times x to the 1, 1 times x to the 3, 1 times x to the 5, and so on. 1 times x to the every odd number. We add them up, and we get the sum over here. I equals 0 to infinity of x to the 2i plus 1. And what we're trying to find here, since we have 100 total candies, we want to find the x to the 100 coefficient of the product of these polynomials. P1 times P2 times P3 times P4 times P5. So we're just going to multiply them together using what we calculated in the last few bullets. So the last few bullets, we got expressions for P1, P2, P3, P4, and P5. So we multiply them together to determine what that product is. And when we multiply them, the P1 and P2, they're both the same polynomial, this 1 plus x. So that's how we got that. The P1 and P2 contributed that. This one right here in the middle, the sum I equals 0 to infinity of x to the I. That's our P3. That's from 2 bullets ago. And from the last bullet, this one right here is P4, P5. And note that we are squaring the first one and we're squaring the last one. That's because P1 and P2 are the same. They're both 1 plus x. So we get a 1 plus x times 1 plus x. which is a 1 plus x squared. Similarly with the P4 and P5, they're both the same. So whatever their value is, that sum, I equals 0 to infinity of x to the 2i plus 1, we're squaring that when we multiply them together. And what we're going to use here, we're going to use the fact that this sum, the sum of x to the 2i plus 1 from I equals 0 to infinity, we can evaluate that sum. And let's see how we evaluate it. So we take the sum up here. We're going to factor out an x. We're going to write it as x times the sum I equals 0 to infinity of x to the 2i. We can now write this, we won't change that, but we'll change inside the sum. I equals 0 to infinity of x squared to the I. And now we can assume that our x is between 0 and 1. So when we're using the generating functions, when we're building these polynomials, it's not important what value of x we're using. So any value of x is fine to use. It's the polynomial, we're not actually using the x's. All we're using is the coefficients of the polynomials. So we're just using polynomial arithmetic to keep track of the coefficients and the coefficients of the products. So when we have 0 less than x less than 1, this sum that I've written right here, the sum I equals 0 to infinity of x squared to the I, we see that 0 less than x less than 1 implies 0 less than x squared less than 1. And we can use that to conclude that the sum I equals 0 to infinity of x squared to the I. So in the video, when we looked at summations of polynomials and geometric series, both finite and infinite, we proved a formula for the sum, assuming that the common ratio in this geometric series has absolute value less than 1. And the value that we found, when our common ratio is x squared, as it is in this sum, we get 1 over 1 minus x squared. And so this is why we're assuming here that 0 less than x less than 1 is just so that we know we have an x value where this summation converges. It's not even important that it converges. All that's important is that we're using polynomial arithmetic here. And this polynomial arithmetic is valid. So this equation is valid. These two polynomials are equal. And we can use this right here. So we had the sum that we were looking at down here, but down here there was that extra factor of x, and we didn't have the factor of x up here. So with that factor of x, we get an x in the numerator instead of a 1, and we still have a 1 minus x squared in the denominator. So that's how we got this term right here. We also had this other term, the sum I equals 0 to infinity of x to the I, and we can use the same thing up here. I equals 0 to infinity x to the I. The common ratio here is x in this geometric series. We see that 0 is less than x is less than 1, so we know that this series converges, and it converges to 1 over 1 minus x. And that's just using the same formula that we proved in the video where we discussed finite and infinite geometric series. And that's just what we have down here. It's exactly that. So we can take that product of the 5 polynomials and we can do some substitution. So let's look at what happened. This first term with the 1 plus x quantity squared, that stayed the same. Nothing interesting happened to that. The second term, this summation, I equals 0 to infinity of x to the I, we substituted from right here in this last bullet, we substituted a 1 over 1 minus x for that, and that's why we got this 1 over 1 minus x. Finally, the last part up here, the square of the sum, I equals 0 to infinity of x to the 2i plus 1. We saw what that sum was right here. We saw that sum simplifies to x over 1 minus x squared. So we substituted the x over 1 minus x squared for the sum inside the parentheses. And we can simplify this. So let's see how that simplifies. So we have a 1 plus x quantity squared right here. 1 plus x quantity squared. We have an x squared from over here. Over here we got an x squared. The denominator, we got a 1 minus x. That's from right here. And then this 1 minus x squared quantity squared. We'll write this 1 minus x squared, this difference of squares, as 1 minus x times 1 plus x. And we're squaring it, so each of those is getting squared. And then we can cancel some stuff out. The 1 plus x squared cancels with this 1 plus x squared. And that leaves us exactly what I claim right here. The x squared over 1 minus x quantity cubed. Okay. So I'm going to erase that little thing I wrote right there so we can see the next bullet. Hopefully it's clear. Okay. So there's the next bullet. So it's a claim about something that we showed in the last video. I claim that we showed in the last video that 1 over 1 minus x quantity cubed is equal to the sum I equals 0 to infinity of I plus 2 choose 2 times x to the I. Now, it'll probably look more familiar if we see it this way. So 1 over 1 minus x quantity cubed, this is the same as the sum I equals 0 to infinity of x to the I, that quantity cubed. And we did show that this is exactly what I wrote. We showed that in the last video. We actually proved something much more general than that. So we proved that 1 over 1 minus x to the k, which is the same as the sum I equals 0 to infinity of x to the I to the k. We proved that this equals the sum I equals 0 to infinity of I plus k minus 1, choose k minus 1, times x to the I. So that generalizes what we claim right here. But we only need it for k equals 3. So that's why we're just using it in the case that k equals 3 right here. And this is something we proved in the last video. We proved it using induction and the hockey stick identity. So since we know the polynomial for 1 over 1 minus x quantity cubed, and we're trying to get the polynomial for x squared over 1 minus x quantity cubed, we can write that x squared over 1 minus x quantity cubed as x squared times 1 over 1 minus x cubed. And we know the polynomial for 1 over 1 minus x cubed. So we can take that polynomial and we can just multiply it by x squared. And that means we can just multiply each term x to the I by x squared. So we can replace the x to the I by an x to the I plus 2. So I plus 2 here, we had an I up there, and that was the only difference between this one and this one. So we just shifted it by 2. It shifted each of the coefficients by 2. Now we're almost done because we're looking for the x to the 100th coefficient. So now we need to plug in 100 for the power of x. So that's not plugging in 100 for I, because we want 100 for the power of x. So we want x to the 100 equals x to the I plus 2. That means I equals 98. And we're looking for the coefficient when I is 98. And we can see what that is. That's just going to be I plus 2 choose 2. So 98 plus 2 choose 2. And that's exactly what we got there. 100 choose 2. And that's the answer. The answer is just 100 choose 2. There's 100 choose 2 ways to split up these candies. So here's a problem for you to think about where you can use generating functions. And it's another problem about candies. This time, let's suppose you have a box of 87 candies. And you have 8 people who want to split up the candy. The first 3 people, they want at most 1 candy. So I just want to emphasize, all 3 of these people, they want 0 candies or 1 candy. Either of those is fine, but nothing else. The 4th and 5th people want any positive number of candies. So they're okay with 1 candy, 2 candy, 3 candies, 4th candies, and so on, but not 0. And this is for each of them. So each of these people is fine with 1, 2, 3, or 4, and so on. Each of the first 3 is okay with 0 or 1. And 6th, 7th, and 8th people, they each want an odd number of candies. So they're okay with 1, 3, 5, 7, and so on. And same question as we were looking at on the previous slide. How many ways are there to split the candies between these people? So let's move on to a similar kind of problem with a different setup. Suppose now that you have 5 people who are trying to leave a $50 tip, and each of them wants to leave an integer number of dollars. The first 2 people, they only want to pay $1 or $3. The third person is okay paying any odd number of dollars. So odd number of dollars, just to emphasize, it's 1, 3, 5, 7, and so on. Any odd number of dollars is okay. And the 4th and 5th people, they have the same rule as each other. They want to pay some number of dollars that's a multiple of 4. So let's talk about what that means. For the number of dollars to be a multiple of 4, we're looking for $0, $4, $8, $12 would be okay, 16, and so on. Any multiple of 4. And similar question to the one we looked at with the candies. How many ways are there to split the tip? So we're going to use generating functions again. And that means we need to build some polynomials. We're going to make polynomials for each person again. And since the first 2 people have the same rule about the tip, each of them is only willing to pay $1 or $3. They both have the same polynomial. So P1 of x is equal to P2 of x. And they're both equal to 1 times x to the 1 plus 1 times x to the 3. So let's talk about that for a second. So both the first 2 people are willing to pay $1 or $3. So this $1 right here, that's how we're getting this x to the 1 right here. X to the 1, it has a coefficient of 1. That means there's one way for person 1 to contribute $1 to the tip. This coefficient of the x to the 3rd, since person 1's willing to pay $3, that means one way right here, the coefficient, one way for person 1 to pay $3. Same with person 2. One way for person 2 to pay $1 over here, and one way for person 2 to pay $3 over there. All the other coefficients for person 1 and person 2, so the x to the 0 coefficient, the x squared, x to the 4th, x to the 5th, and so on, all of those are 0 coefficient because there's no ways that person 1 or person 2 is willing to pay $0 or $2 or $4 or $5 and so on. The only dollar amounts they're willing to pay are 1 and 3. So the only non-zero coefficients we get are 1 times x to the 1 and 1 times x to the 3. And we can simplify this to x plus x cubed. So that's the same polynomial for both person 1 and person 2. It's just x plus x cubed for both. Let's look at the polynomial for the third person. Third person, they only want to pay an odd number of dollars. Odd. So remember odd, it's like 1, 3, 5, 7, and so on. So the coefficient of x to the 1. 1 is a possible number of dollars that the third person is willing to pay. So that means that there's one way for them to pay $1. So we got a coefficient of 1 in front of x to the 1. Same with x to the 3. The third person, they're willing to pay $3, and there's one way they'll pay $3. So we get a 1 in front of x to the third. And it keeps on going like that with the even numbers. We get 1s in front of x to the, oh, I said even. I meant odd. These are all odd numbers, 1, 3, 5, 7, and so on. So in front of the odd powers of x, we're getting coefficients of 1. In front of all the other powers of x, we get coefficients of 0 because all the other powers are even powers. And person 3 is not willing to pay an even number of dollars. So there are no ways that person 3 is willing to pay any even number of dollars. So all the coefficients of the even powers are 0. So we haven't written them because 0 times anything is 0, and 0 plus anything doesn't change it. And we can take this sum here, the sum of 1 times the odd powers of x, and we can write it more succinctly as the sum from I equals 0 to infinity of x to the 2i plus 1. We have one more polynomial to calculate. It's the same polynomial for both the fourth and fifth people. And their polynomials, P4 and P5, they're going to have one coefficients in front of all the powers of x that are powers of x which are multiples of 4. So x to the 0, x to the 4th, x to the 8th, x to the 12th. All of these, they get one coefficients in front of the power of x because person 4 and person 5, they're willing to pay $0. They're willing to pay $4. They're willing to pay 8, 12, 16, and so on. They're willing to pay any number of dollars that's a multiple of 4. So there's one way for them to pay $0, one way for person 4 to pay $4, one way for person 4 to pay $8, one way for person 4 to pay $12, and so on. Same with person 5. One way to pay $0 for person 5, one way to pay $4 for person 5, and so on. They both have the same polynomial. And it's an infinite polynomial. It's a sum that we can write in this way as I equals 0 to infinity of x to the 4i. And like we did with the last problem, we're going to multiply all these polynomials together, and we're going to look for a certain coefficient. The coefficient we're going to look for, it tells us up here, is the x to the 50th coefficient. So that's what we want, is the x to the 50th, same as the total number of dollars in our tip, x to the 50th coefficient of the product of all 5 of these polynomials. And the good thing is we already calculated these polynomials. We got expressions for them in the last few bullets. So we can do some substitution here. So we substitute the first one, that x plus x cubed quantity squared. That's from the P1 and P2. So each of P1 and P2 of x, both of them are equal to x plus x cubed. So when we multiply P1 of x times P2 of x, we just get the square of x plus x cubed. This sum right here, the sum I equals 0 to infinity of x to the 2i plus 1, that's the same sum we saw here. That's just from the P3, that is P3 of x. And finally, this sum right here that we're squaring, that is exactly what we saw in the last bullet. This is from P4 and P5. So both P4 and P5 of x are equal to this sum from I equals 0 to infinity of x to the 4i. So P4 of x times P5 of x is the square of that sum. And we can simplify a little. So let's see how this simplifies. So first, we can take this sum, I equals 0 to infinity of x to the 2i plus 1. Again, we're going to assume that 0 is less than x less than 1 so that these sums will converge. So this sum from 0 to infinity of x to the 2i plus 1, like on the last slide, we'll factor that x out, of x to the 2i now. And we can write that as x times the sum I equals 0 to infinity of x squared to the I. And then we can simplify this to x over 1 minus x squared. Okay, and that's how we got this term right here. So the first term, the x plus x cubed quantity squared, that was the same as what we saw in the previous line. The second term, we substituted for the sum I equals 0 to infinity of x to the 2i plus 1. We substituted just this x over 1 minus x squared. That's how we got this middle term here. And this last term right here, this 1 over 1 minus x to the 4th quantity squared, we can see that the sum I equals 0 to infinity of x to the 4i, we can write that as the sum I equals 0 to infinity of x to the 4th raised to the I. And using the same formula that we proved in the video on geometric infinite series, the value of this sum when it converges, and it does converge when 0 is less than x is less than 1, the value is going to be 1 over 1 minus x to the 4th. And we were squaring that sum over here, so we're squaring the 1 over 1 minus x to the 4th over here. So that's how we get this last term, the 1 over 1 minus x to the 4th, and we're squaring it. And we can simplify a bit more here, so I'll erase so that is legible. So let's see why this part is true. So we have x plus x cubed quantity squared. We have an x divided by 1 minus x squared. And we have a 1 divided by the square of 1 minus x to the 4th. So we can write this by factoring out an x here. We can write this as an x times a 1 plus x squared instead of an x plus x cubed. And we're squaring everything. So we got an x squared, and we have a 1 plus x squared quantity squared. Okay, so we dealt with that first term. Second term, we won't do anything. Leave it as is. And then the last term, we got a difference of squares right here. We'll factor it. We'll write this as 1 over 1 minus x squared times 1 plus x squared. And we're still squaring that difference of squares. We got that 2 there, so we're squaring both of these terms. We can cancel some stuff out here. We got a 1 plus x squared quantity squared. That cancels with the 1 plus x squared quantity squared down here. And the numerator, we're left with x cubed. And the denominator, we have a 1 minus x squared times a 1 minus x squared squared. This gives us a 1 minus x squared quantity cubed. And that's exactly what we see right here. And we're pretty close to the end. We just need to do a little bit more algebraic manipulation. And I'm going to need to clear some space so we can see the last couple bullets. So in the last video, when we started talking about generating functions, we proved this result, which I mentioned on the earlier slide, that the polynomial 1 divided by 1 minus x cubed, which is the same, recall that's the same as the sum I equals 0 to infinity of x to the I, that cubed. So same thing. We proved in the last video that this is the same polynomial. the sum I equals 0 to infinity of I plus 2 choose 2 times x to the I. So we can simplify this polynomial here, which is the same as this. It simplifies to that. And we proved that in the last video. And again, like I mentioned earlier, we proved it in more generality than that. We proved it for any power here, not just 3, but any power k. We proved that the coefficients are going to be I plus k minus 1, choose k minus 1. And we're going to use this here. So we have up here the polynomial whose coefficients we're trying to find. Instead of a 1 minus x cubed in the denominator, we have a 1 minus x squared quantity cubed. So we want to go from a 1 minus x to a 1 minus x squared, and the cube part right here is still the same. So if we know what 1 over 1 minus x quantity cubed is, in order to get 1 over 1 minus x squared quantity cubed, we can just plug in x squared for all the x's in this sum right here. So this sum was for 1 minus x, and then cube that bottom part. This right here has an x squared in the place of the x. So we took the x here, we replaced it with an x squared. All we have to do is replace all the x's here with x squareds. So we're gonna get, so our new sum is gonna be I equals 0 to infinity of I plus 2, choose 2, and then x squared. We just replace that x with the x squared, and we're raising that to the I still. X squared to the I is the same as x to the 2i. So x squared to the I, x to the 2i, the same thing. So this is how we got this sum right here. So this sum is the sum when we have a 1 over 1 minus x raised to the third. And this right here is a sum when we replace the x in this sum with an x squared. So the x to the i's became x to the 2i's. Okay, and just one more bullet, or one more part of a bullet. So now that we know what is the polynomial for 1 over 1 minus x squared quantity cubed, we can calculate the polynomial for x cubed over 1 minus x squared quantity cubed. And this is just equal to x cubed times 1 over 1 minus x squared quantity cubed. So we can take the polynomial for 1 over 1 minus x squared quantity cubed, and we can just multiply it by x cubed. So that's taking the x cubed times each x to the 2i. So we can take the x to the 2i, and we can just add 3 to its exponent. And that gives us an x to the 2i plus 3. So the only thing that changed between this sum and this sum is just the exponent of the x. And we're looking for the coefficient of x to the 50th in this sum. So we want x to the 50th in, and let's write that sum out a little. So the I equals 0 term of that sum, we're gonna get 0 plus 2, choose 2. So it's gonna be 2 choose 2 for I equals 0. And then x to the third, x to the 2 times 0 plus 3. The I equals 1 term, that's gonna be 1 plus 2 choose 2, so 3 choose 2, times x to the 2 times 1 plus 3, so we get x to the 5th. The 2 term is going to be 4 choose 2, because it's 2 plus 2 choose 2. And we get x to the 7th, because 2 times 2 plus 3, and so on. We see that all of the terms with non-zero coefficients, so all non-zero terms have odd x powers. So we look at this polynomial right here, we see that the even x powers have coefficients of 0. The odd x powers have coefficients, these binomial coefficients. So the odd x power 2i plus 3 has a coefficient I plus 2 choose 2. But all of the even powers, so even powers like x to the 0, x to the 2, x to the 4, x to the 6, and so on, none of them show up in this polynomial. All of them have coefficients of 0. That means the coefficient of x to the 50th in that polynomial is just 0. So the fact that the coefficient of x to the 50th in this polynomial is 0, that means that the number of ways to split the tip so that it satisfies the requirements for these 5 people is 0. So the answer to this problem is 0. Before we go to the next slide, let's talk more about why the answer is 0, why it makes sense. So these first 2 people, they only wanted to pay $1 or $3, and both $1 and $3, these are both odd numbers of dollars. So these are both odd. We already knew the third person, they're only willing to pay an odd number of dollars as well. And the fourth and fifth people, they're only willing to pay a number of dollars that's a multiple of 4. Multiples of 4, they're even. So we were trying to find some way to find 3 odd numbers and 2 even numbers that add up to 50. So we were trying to get some 3 odds, odd plus odd plus odd, plus even plus even. And we wanted that to equal 50, which is even. And I claim that's impossible. I claim if you have an odd number plus an odd number plus an odd number, that's going to give you an odd number, the sum of 3 odds. And if you add 2 evens to that, it's still going to stay odd. So you can never get an even. You can never get 50. So that's another way we could have seen that $50 tip was impossible based on the constraints that these people were requiring. Okay, so let's move on to the next slide. Next slide is going to be a problem for you to think about. And this problem is pretty similar to the one we just talked about. Suppose now that you have 7 people, and in total they want to leave a $90 tip. The first 2 people, they're only willing to pay $1 or $4. The third person is willing to pay any number of dollars that's a multiple of 3. So for example, 0 is fine, 3 is fine, 6 is fine, 9, 12, 15, and so on, forever. The fourth and fifth people, they're only willing to pay $2 or $8. And then the sixth and seventh people, they're only willing to pay $1 or $10. And the question, same question as the previous slide, how many ways are there to split the tip between these people? And here's a second problem for you to think about. This problem, similar kind of problem, but some different constraints here. Suppose for this other problem, you have 6 people and they want to leave a $120 tip. And here's the rules for the first 2 people. They only want to pay $1 or $14. Suppose the third person is willing to pay any amount of money. And the fourth and fifth people, they're both willing to pay either $2 or $17. And the sixth person, say that they are only willing to pay $1, $3, or $10. And same question as the previous problem, how many ways are there to split the tip between these people? Now let's look at another kind of problem. This kind of problem is a problem where we're going to count the number of solutions to a certain equation. The equation is called the Diophantine equation. So typically, these equations have 2 or more unknowns, and we're looking for integer solutions of them. This one in particular is a linear Diophantine equation because all of the powers of our unknowns are 0th powers or 1 powers. We have some extra constraints on x, y, z, and w besides the fact that they're integers. So we're going to require that 2 is less than or equal to x is less than or equal to 3. We'll also require that 4 is less than or equal to y is less than or equal to 5. 6 is less than or equal to z is less than or equal to 7. And W can be anything between 0 and 10 inclusive. And just to emphasize again, they're all integers. So X here can be 2 or 3. Y can be 4 or 5. Z can be 6 or 7. And W here can be anything, 0, 1, 2, up to 10. So anything between 0 and 10 inclusive. And we're going to try to find the number of integer solutions for X, Y, Z, W, the tuple. Like we did with the candy problem and with the tip problem, we're going to make a polynomial for each of the variables. So here, instead of having people, we have variables. So each of these variables is going to get their own polynomial. Since one of our variables is x, and in the previous slides we were using x as a variable in our polynomials, we're going to have to use a different variable in our polynomial. Instead of using an x, I will use a t. So let's look at what our polynomial for x should be. This will be called p sub x of t. So x is the label, and t is the variable of this polynomial. And this polynomial is going to be t squared plus t cubed. Why is that? Well, we can write the t squared plus t cubed. This is the same as 1t squared plus 1t cubed. And the square and the cube, let's look at that, the 2 and the 3. These are the possibilities for x. There's one way that x can be 2, and there's one way that x can be 3. So we have a 1 in front of the t squared, the number of ways for x to be 2, and the 1 in front of t cubed, number of ways for x to be 3. And that's our p sub x polynomial. All of the other coefficients for like t to the 0, we have a coefficient of 0 there. T to the 1, also a coefficient of 0, because x cannot be 0 or 1. T to the 4th, also 0. So all the other powers of t, they have 0 coefficients. So we don't need to write them because zeros don't do anything. The polynomial for p sub y, we can calculate that one similarly to how we calculated the p sub x polynomial. So we see we have a t to the 4th and a t to the 5th here. The 4 here is from that 4 up here. The 5 here is from the 5 up here. The coefficient of the t to the 4th and t to the 5th and p sub y, both of the coefficients are just 1, because there's one way for y to be 4, and there's one way for y to be 5. And all the other coefficients of any other powers of t besides the 4 and 5 powers, all of those other coefficients are just 0, because there's no way for y to be anything except for 4 or 5. Now let's look at the p sub z polynomial. This one, very similar calculation to p sub x and p sub y. It's just t to the 6th plus t to the 7th. So we have 6 and 7, same as we see up there, the possibilities for z. There's one way for z to be 6, there's one way for z to be 7. So the coefficient of t to the 6th is 1, the coefficient of t to the 7th is 1, and the coefficient of any other power of t is 0, because t can't be, because z can't be anything besides 6 or 7. So our p sub z polynomial, the only coefficients that are non-zero are the coefficients for t to the 6th and t to the 7th. And all the other coefficients are 0, because 6 and 7 are the only possibilities for z. So those are our first three polynomials for the x, y, and the z variables. And the constraints for x, y, and z are all pretty similar. X, y, and z are all restricted to only have 2 possible values. For the w polynomial, this one's different from the first 3. This one is just going to be 1 times t to the 0 plus 1 times t to the 1. I'm going to circle these exponents, plus 1 times t to the 2, and so on, up to 1 times t to the 10th. Notice this 0, 1, 2, up to 9, 10. This is the same thing that we see right here. These are the possible values for w. So all the possible values for w, the power of t corresponding to that value has a coefficient of 1. There's one way for w to take on that value. Any power of t which is not equal to t to the 0, t to the 1, t to the 2, all the way up to t to the 10. So any power of t beyond 10, like t to the 11th, t to the 12th, and so on, all of those coefficients are 0, because there's no way for W to take on any of those values beyond 10. So we get this polynomial, 1 plus t squared plus t cubed, all the way up to t to the 10th. And that's our piece of W polynomial. Now our equation was x plus y plus z plus w equals 16. 16, we want that to be the sum of the x, the y, the z, and the w. So what we want to do is, just like the previous problems, we're going to multiply our polynomials together, and we're going to look for the coefficient of a certain power of t. The power of t that we're going to want to find is the t to the 16th. So we're looking for the coefficient of t to the 16th in p sub x of t times p sub y of t times p sub d of t times p sub w of t. And we calculated each of those polynomials in the last two bullets, so we can just substitute here to evaluate this product. And when we substitute, we multiply those four polynomials together. And you can do that by hand if you want. It's not too bad to do by hand, but you're also welcome to use a calculator or a computer or a website, any website you want, like Wolfram Alpha, for example, would be fine. And when you multiply these polynomials together, you get t to the 25th plus 4t to the 24th plus 7t to the 23rd. And then for the terms from t to the 22nd all the way down to t to the 15th, all of the coefficients are 8. And then t to the 14th has a 7 coefficient, t to the 13th has a 4 coefficient, and t to the 12th has a 1. So our coefficients go 1, 4, 7, a bunch of 8s, and then 7, 4, 1. And we're looking for the t to the 16th coefficient in this polynomial. So we can circle t to the 16th. We look at its coefficient. It's the same coefficient as a lot of the other coefficients. The coefficient here is 8. So that tells us the number of integer solutions for the Diophantine equation at the top, number of integer solutions that we were looking for this equation with these constraints here is going to be 8. So we have 8 integer solutions, x, y, z, w. Now, there was a way to see that there was 8 integer solutions that is a little faster than using the polynomials. So let's talk a little bit about that. So I claim that any possibilities for x, for y, and for z can be combined together to give us a possibility for x, y, and z. So more specifically, x, y, and z, each of them has 2 possibilities. The x, its 2 possibilities are 2 and 3. The y, its 2 possibilities are 4 and 5. The z, its 2 possibilities are 6 and 7. So the number of possibilities for each of those 3 variables is 2. The number of possibilities for x, comma, y, comma, z, this tuple, the number of possibilities is going to equal 2 and raised to the 3rd, because each of x, y, and z have 2 possibilities, and there's 3 of them. So we're multiplying 2 times 2 times 2. That's 8. So there's 8 total possibilities for x, for y, for z. Now, in order for x plus y plus z plus w to equal 16, we need w to equal 16 minus x minus y minus z. We can solve for w just by subtracting the x, the y, the z from both sides. So in order for that equation to be true at the top, this Diophantine equation, we must have w equal to 16 minus x minus y minus z. So I claim that each tuple x, y, z gives us at most one solution x, y, z, w, because there's only one value of w that can be combined with the values of x, y, and z to give us a sum that's 16. I claim something stronger though. I claim that each possibility for x, y, z, not only does it give us at most one solution x, y, z, w, it gives us exactly one solution x, y, z, w. So what we need to show here is that any w we get by calculating as 16 minus x minus y minus z is going to be a valid w. It needs to be in the range for w. So what we're trying to show, I'm going to write it up here, and then we'll talk about why this is true. We need to see why 16 minus x minus y minus z is in the range for W. In other words, both of these question marks, y is it less than or equal to 10? And y is it greater than or equal to 0? And we'll look at both those questions. So to see why it's greater than or equal to 0, we can first find an upper bound on x plus y plus z. If we want to find an upper bound on x plus y plus z, we can look to see what's the greatest possible value of x. The upper bound on x is 3. So we can write a 3 there. The upper bound for y is 5. Y can be at most 5. So we can put a 5 right here. And the upper bound for z is 7. Z can be at most 7. So we can put a 7 here. And 3 plus 5 plus 7 equals 15. So we see that x plus y plus z is less than or equal to 15. That means that 16 minus x plus y plus z is going to be greater than or equal to 16 minus 15, which equals 1. And 1 is greater than or equal to 0. So we just found that 16 minus the quantity x plus y plus z is greater than or equal to 0. So that gives us this first inequality that we want to check. So I'll get rid of the question mark there. Let's check this second inequality now. So in order to see why that's true, we want to prove instead of an upper bound on x plus y plus z, we want to find a lower bound on x plus y plus z. So x plus y plus z, I claim we can find a lower bound as well. We can say it's greater than or equal to, and we can take the lower bound for each variable. So x is at least 2, so put a 2 there. The y is at least 4, put a 4 here. And the z is at least 6, so we'll put the 6 right there. We add them up, we get 12. So x plus y plus z is at least 12. That means that 16 minus x plus y plus z is going to be less than or equal to 16 minus 12, which is equal to 4. And that's clearly less than or equal to 10. So we see that for any x, y, and z that satisfies these three constraints, the number 16 minus x minus y minus z is in the range for w. It's between 0 and 10, which means that it's a valid choice for w. So it gives us a solution x, y, z, w. So the number of solutions x, y, z, w was just the same as the number of possibilities for x, y, and z. So that's another way to see why we got 8. And it's a very different solution, but we got the same answer. Okay, so I'm going to erase that so we can look at the next slide. And the next slide is another problem for you to think about. Here's another linear Diophantine equation. X plus y plus z plus w equals 25. X, y, z, and w are all integers. And here's some constraints on them. 2 is less than or equal to x is less than or equal to 3. So x can be 2 or 3. Y is odd, so y can be 1, 3, 5, 7, 9, so on. Z is greater than or equal to 3, so z can be 3, 4, 5, 6, so on. And w is greater than or equal to 5, so w can be 5, 6, 7, 8, and so on. And I just want you to find the number of integer solutions for this tuple x, y, z, w. So let's look at one more type of problem where we can use generating functions and get the answer pretty easily. So suppose we have unlimited coins and they're worth either $2 or $5 each coin. And each of these types of coins, the $2 coins and the $5 coins, there's unlimited of each of those types. And the question is, how many ways can we pay $15 using these coins? So, like I said, it's going to be another problem where we're using generating functions. So we're going to want to build some polynomials. We're going to want to multiply them together. And we're going to want to find a certain coefficient. So the polynomials we'll make two polynomials here because we have two types of coins. We're gonna have a polynomial for the $2 coins and another polynomial for the $5 coins. This polynomial for the $2 coins right here, this gives us the number of ways to make an amount out of $2 coins. So this first term, the 1, we can write this as 1 times x to the 0. The second term, the x squared, we can write that as 1 times x squared, 1 times x to the 4th, 1 times x to the 6th, and so on, dot, dot, dot. So this number right here, the 1 times x to the 0, that's saying that using the $2 coins, there's one way that we can make $0. That's just by using no $2 coins. This term right here, the 1 times x squared, this is saying that there's one way to make $2 using the $2 coins, just by using a single $2 coin. This term right here, it's saying that there's one way to make $4 using these $2 coins, and that's by using two of the $2 coins. This term right here, there's one way to make $6 using the $2 coins. Just use three $2 coins. It keeps on going like that. So we get 1 times every even power of x, because the $2 coins, we can only make even numbers of dollars with $2 coins. And each even number of dollars, there's one way to make that with $2 coins. And we can write the sum in a more concise way as the sum from I equals 0 to infinity of x to the 2i. So that's our first polynomial. Second polynomial, p sub 5 of x. This is going to be, well, we can write this like we did for the p sub 2. So we have a 1 times x to the 0 plus 1 times x to the 5 plus 1 times x to the 10th plus 1 times x to the 15th, and so on. So this first term, 1 times x to the 0th, there's one way that we can make $0 using the $5 coins. We just use no coins. This term, 1 times x to the 5th, there's one way to make $5 using the $5 coins. We just use a single coin. 1 times x to the 10th here, there's one way to make $10 using the $5 coins. We use two coins. Here, there's one way to make $15 using the $5 coins. We use three coins, and so on. So we get any powers of x that are multiples of 5 have a coefficient of 1. Any powers of x that are not multiples of 5 get coefficients of 0, because you can't make any amount of dollars that's not a multiple of 5 if you're only using $5 coins. When we simplify this sum, or when we write it more concisely, I should say, we write it as the sum I equals 0 to infinity of x to the 5i. And now we're just going to multiply these polynomials together, and we want to find a certain coefficient. The coefficient we want to find is the amount of money we're trying to make, the 15. So we're looking for the coefficient of x to the 15th in the product of these polynomials, p2 of x times p5 of x. So we can look at p2 of x and we can look at p5 of x. Maybe I'll write a few more entries of them. So 1 plus x squared plus x to the 4th plus x to the 6th plus x to the 8th plus x to the 10th plus x to the 12th plus x to the 14th, and so on. Any of the higher terms in p2 of x won't affect anything with an x to the 15th coefficient, because they will be too high in their power of x. p5 of x, we can write that 1 plus x to the 5th plus x to the 10th plus x to the 15th, and so on. And we want to try to find how to get x to the 15th by multiplying these together. So if we have this one term up here and we want to get an x to the 15th by combining with some term down here, the only term we can combine it with is this one right here. And we can look at the same thing right here, this one right here. This one, if we want to combine it with an x to some term from the top, from P2 of x, to make an x to the 15th. We see that in P2 of x, there's no term that's going to make an x to the 15th with this 1. So there's nothing to pair this with. This one's going to be useless. This x to the 5th right here, we can see, can this be paired with anything? X to the 5th, it can be paired with something. So we want to find something so that x to the 5th times that term gives us an x to the 15th. And what we're looking for is an x to the 10th, which is right here. So we have an x to the 10th to pair with that x to the 5th. Then we can look at this x to the 10th right here. This x to the 10th would need an x to the 5th to make an x to the 15th. There's no x to the 5th up here. So this x to the 10th can't be paired with anything. So I'll put a slash through it since it can't be paired. I'll put a slash through this one since it can't be paired either. Any other terms down here past the x to the 15th would be too large in their power of x to make an x to the 15th in the product of P2 of x times P5 of x. So we were only able to make 2 pairs in order to get an x to the 15th. We were able to pair the 1 with the x to the 15th. We were able to pair the x to the 5th with an x to the 10th. So we take, to get the coefficient of x to the 15th, it's just going to be the sum of the products of the coefficients in these 2 pairs. So we get 1 times 1 plus 1 times 1. And that gives us 2. So that's our coefficient of x to the 15th. And let me clear that so it's actually legible. Okay. Yeah, so the coefficient is 2. So we can actually just multiply those polynomials together. And the polynomials, so we can't multiply them together if we have them go to infinity. But if you cut them off, so if you make, instead of infinity here, if you make this a 15, and you make this a 15, then you can multiply them together. And for this one, you don't actually have to go up to 15. You can go up, instead of 15, you can go up to 7. So it only needs to go up to x to the 14th. And once you get to I equals 8, that's already x to the 16th. So you wouldn't be able to get an x to the 15th with that. This one right here doesn't have to go up to 15th. You can actually go even lower than that. You can go up to 3. So when I equals 3, you get x to the 15th. Any higher I than that, and the power of x is too large. So if you want to just do this by hand or using a computer or calculator, you can actually just multiply this polynomial times this polynomial. And that will give you the correct coefficient. But what we just did to find the coefficient when we multiply the infinite polynomials is also a perfectly valid way to do it. So usually with these kind of problems, like we saw with lots of other problems, there's multiple ways. So we got a coefficient of 2 for the x to the 15th coefficient of the product of these polynomials. And that tells us since the coefficient is 2, the number of ways to pay $15 using these coins is just 2. So the only ways that we can make $15 using these coins is we can do 5 times $2 plus 1 times $5, or we can do 3 times $5. And those are the only ways we can make 15 using just $2 and $5 coins. So before we finish this video, here's another problem for you to think about that's very similar to this coin problem. It's just we're adding in another kind of coin. So suppose that we have unlimited coins of each of these types, where the types are $3 coins, $5 coins, and $7 coins. And the question is, how many ways are there to pay $20 using these coins? And that brings us to the end. Thanks for watching.